Hi. Today we're going to talk about permutations as an initial foray into the wide, fascinating world of probability theory. You might be asking, well, why do we need to know about probability? It's all like abstract, right? It's big science, math. I'm not going to work on Wall Street. I need to know about probability. Well, probability and modeling probability occurs all the time in all our aspects of life. Say, three friends are going to a dinner, right? Nice, fancy dinner. And they have 3 seats laid out, right? I'll call these friends Arthur, Bob, and Kathy. We have seats 1, 2, and 3. So how many ways can 3 friends sit in 3 seats, right? And at first I might say, oh, well, but, just one, and, here, and here, right? We can have Arthur sit in the first one, Bob sit in the second one, and Kathy sit in the third one. Well, that's not necessarily true, because we could also have Arthur sit in the first one, but Kathy and Bob could switch seats, and that's still valid. Or we could have Bob on the first one, and then Arthur, then Kathy, or Bob, then Kathy, then Arthur, then Kathy, then Bob, then Arthur, or Kathy, then Arthur, then Bob. And then we say, wow, it's a lot of seats. It's a lot of scenarios. That's, all in all, 6 total combinations, right? So there were 6 total ways that these 3 people can sit in these 3 seats. And at first, doing this may seem like, wow, what's the big deal? What do we gain from this? Well, permutations allow us to figure out how we can order any set of objects. And that's really important, because in any large-scale operation, you're going to have a lot of things and a lot of places to put a lot of things. And you need permutations to give you a sense of how many ways can I do something, right? Once you know that, you can learn a lot more about, oh, well, I can package these 6 things in these X ways. It's very valuable for a wide variety of fields, and most importantly, just the abstract. But now we have this, and what really are we going to do with it? What value has this produced? Well, we notice that this strategy works pretty well for what we were trying to do, right? This is a basic permutation where we just write out all the possible solutions, right? Well, what if there were 100 people eating dinner at a restaurant and there were 100 seats? That would be a lot to write out, right? We'd have 100 seats all the way over here, and then 100 people to order in all the seats. That's a lot of work to think about all the possible combinations of people that could sit in those seats. But let's look at this closer to see if we can identify an easier way. All right, so I notice, right, hey, there are 3 possible people who can sit in the first seat, right? Arthur, Bob, Kathy. Right, so we can say, hey, there's 3 people who can sit in this first seat, right? And then we notice, hey, for each of these ones after, there are 2 people who can sit in the next seat, right? If Arthur's sitting in the first seat, then Bob or Kathy can sit in the second seat. If Bob's sitting in the first seat, either Arthur or Kathy can take the next seat. No. So there are 2 possible people who can sit in the second seat. And now, hey, we've got 1 person sitting in the first seat and 1 person sitting in the second seat. That means there's only 1 possible person who can sit in that final seat, right? Because if Kathy and Bob, for example, are sitting in the first and second seat, well, then Arthur has to sit in the third seat, right? And if we want to say, well, how many arrangements are possible, right? Well, we simply multiply, because there are 3 possible people who can sit in the first seat. For each of them, right? For each of Arthur, Bob, and Kathy, there are 2 other people who can sit in the second seat. And then for each of them, there is only 1 possible person who can sit in the third seat. So we multiply. And 3 times 2 times 1 is 6. Or we can write that as 3 factorial. And what this factorial means, this little exclamation part, is a little fun part of math. It's not the number yelling at you. It's just basically saying, multiply this number by every number preceding it until you get to 1. Right? So, for example, if I had something like 6 factorial, that'd be 6 times 5 times 4 times 3 times 2 times 1, right? That's just what that factorial means. But let's say we wanted to make this a little more interesting. Say we didn't have 3 people with 3 chairs. Say we had 5 people. Arthur, Bob, and Kathy are still there, but now they're joined by David and his good friend Egbert. But there are still only 3 seats left. And this is where permutations come in extra handy. They're for dealing with situations where you have too many people or too many things put in too many locations and too few locations. And you have to make decisions. You have to know, well, what are the possible outcomes that could come from me putting 3 people of these 5 people in those seats? So how am I going to do this? Right, how am I going to do this? Well, I'm going to think about the strategy that I tried earlier. Right? I knew last time if I had 3 people on 3 seats, well, that would leave 3 people that could sit in the first seat, 2 people that could sit in the second seat, and 1 person who could sit in the third seat. And that logic still kind of applies. Right? I have 5 people. Any of them can hop down and take that first seat. That leaves 4 of them that can do the same for that second seat. And then there's 3 people who are not sitting, so 3 more people, 3 different people could also sit down, right? And of course, we multiply them. Because, if Arthur, any of these 5 people sat down, right, then any of these other 4 people could also sit down. And to gather all these possibilities, we multiply them together, right? So we have 5 times 4 times 3, which is 60. But interestingly, we notice another way of writing this would be 5 factorial, right? 5 times 4 times 3 times 2 times 1 over 2 factorial. So if you think about it, right? Just writing this out. We sure enough do cancel this out. So we can say, hey, this number that we got is equal to 5 factorial over 2 factorial. And that's interesting. Because that's the same thing as saying 5 factorial over 5 minus 3 factorial. That's very interesting because we have 5 people and 3 seats. And this is the formula we use for permutations whenever we want to solve them, right? We have the number of things, of people in this case, that we have, factorial, over that number minus the number of objects we want to associate them with or group them with, minus that, right? So we have the total number of objects, factorial, divided by the total number of objects minus the number of objects that we've selected, factorial. So in this case, we have 5 total people, right? Then of those 5 people, we're selecting 3 of them to go sit in one of these 3 chairs, right? So in this case, the n would be 5, and the 3 would be r, which sure enough goes out to produce our 5 times 4 times 3 as we saw earlier. Now, another interesting thing, though not necessarily applicable, but to the wider world, but still pretty interesting, is permutations and letters. Now, there are a lot of words in the English language, but we can actually quantify a lot of them down to certain things, right? And to get my point, let's say we have the word tiger. How many ways can we arrange the letters of the word tiger to produce a new word? And in this case, we're not going to worry about whether the word's actually a word or not, right? It could be something like geit, which is not a word, but it's still an arrangement of letters. So how are we going to do this? Well, we have 5 letters and 5 spots to put them in. Now, we could say, hey, I have 5 letters that I can choose to put for the first letter. I have 4 letters that I can choose to put for the second letter, and then 3, and then 2, and then 1, and we can just multiply them all together, which is the same thing as 5 factorial, or 120. Or you can say, hey, we have 5 objects, right? 5 letters in this case, and we're selecting 5 of them. We can also say, hey, we have 5 letters, and we're choosing 5 of them, so our R is 5 in this case. So we have 5 factorial over 0 factorial, which is 5 factorial. You might say, oh, hold up, it's a 0. I can't divide by 0. That just doesn't work, right? That breaks math. I put in 5 divided by 0 into the calculator, and I will get an error. But here is something that I find particularly interesting. 0 factorial is always equal to 1. And you might say, well, why is that, right? Well, think about in the context that we're using it, right? We're using this in relation to permutations, or the ways or that we can group things into sets and order them and know how many arrangements of objects we can have. Right? If we have an empty set, right, where there's nothing, well then how many ways can you order nothing? One way. There's only one way to order nothing, and that is just it. So 0 factorial is equal to 1, which is why we don't have to worry about dividing by 0, which would be a huge headache. We can just skip right over it. Now, to make this a little more interesting and to use our permutation formula, let's say I want to choose 3 letters out of tiger to create a new word. In this case, it's a lot easier to use our permutations formula. I know I have 5 letters total, right? And I'm choosing 3 of them to form my new word. That's 5 factorial over 2 factorial, which is just 5 times 4 times 3, or 60. There we go. Now, the trickiest challenge yet, and we get to see the extent of this logic, right? Let's say we have the word Mississippi. All right. Trying to remember how to spell Mississippi so I don't spell it wrong. And let's say we want to find out how many permutations there are of the word Mississippi. Now, we could say how many total arrangements are there, et cetera, et cetera, et cetera. And this seems pretty intense. But we'll start with our usual strategy, right? We have 11 letters, so we'll make 11 lines. Right? Now, we can choose, 11 words in the first one, and then 10 words in the second one, and so on and so forth, until we eventually get 11 factorial. You might say, oh, that's our answer. Thank goodness that's easy. Well, that's not true, because these aren't all the unique arrangements of the letters in Mississippi, right? For example, what would happen if I switched the second letter of Mississippi with the 5th letter of Mississippi? I'd just be swapping those 2 I's. Would that create a difference? Would that change the word Mississippi? No, it'd be the same exact word. So this method of just multiplying all of them out to get a factorial doesn't work, because doing this would include words like this, right? Where I just swap these 2 letters. It doesn't change the word, it's still Mississippi, so I need to do something different, right? I need to account for all of these duplicate letters, right? These 4 I's and these 4 S's and these 2 P's. I need to deal with them. So, how am I going to deal with them, right? So let's start with the P's. Right? For every permutation we can make an identical permutation with the P's just swapped. Swapping those P's doesn't change the word, right? If I have, Mississippi here, I flip these 2 P's, it's the same word. It doesn't change it, right? So to account for this, I need to take all my possible permutations and then divide them by the number of ways we can arrange the 2 P's, which is just 2, right? If you think about it this way, hey, I need to put 2 objects in, I need to 2 objects, and I'm choosing 2 of them, right? That's 2 over 2 minus 2, which is just 2 factorial, right? And the same logic applies to my s's and my i's, right? In this case, they're bigger, right? I have 4 s's and i's, and I'm choosing 4 of them. That's, that my n in this case is 4, and my r is also 4, since I'm choosing 4 of them, which is again 4 factorial. So that's 1 for the s's, and that's 1 for the i's. Right? And this is the number of the permutations of the word Mississippi, where there isn't something stupid and weird and like a duplication like this, right? Where we just swap the i's, we swap the p's, but we didn't actually change the word. And if we do all this out and cancel out these extra factors right here, our answer would be 34,650. That means there are exactly 34,650 ways to arrange letters in Mississippi to create a new word. So, that is the wonder of permutations. A way to order your world and find out exactly and quantify exactly how many ways can you do something. Exactly how many ways can you put something in something else. And that's permutations. Thank you for watching. I hope you have a great day.